Welcome to lecture number 20. We are studying stochastic processes and we'll continue studying Markov processes in this lecture. In our last lecture, we studied recurrent and, and transient classes. A class is a state is recurrent if a state is recurrent if it is in if it is in the set of accessible states of all the states that are accessible from that very state. Uh, in this lecture, we will study periodicity. For more about recurrent and transient states, you are referred to my previous lecture, SP19 and SP18. Right. A recurrent class is said to be periodic. Today we'll study periodicity. Periodicity. A state is a class of states, a class of recurrent states. Periodicity is defined only for recurrent states, not for transient. A class of recurrent states means the class will contain more than one states and they are said to be periodic. A class of recurrent states is periodic if its states can be grouped in various groups. Suppose we have these states, maybe these three states which are all recurrent, so we can have these in one set and this one in one set. So we may have more than one sets of a given class of recurrent state. So we have studied that there can be different classes of recurrent states in our last lecture, the 19th lecture. So the recurrent class, a given recurrent class can further be divided into subsets where subsets can contain different number of states. Right. So a recurrent class is periodic. I repeat, a recurrent class is periodic if the states in that recurrent class can further be divided in groups, and we call those groups as S subsets, S1, S2, S3, up to SD. Into disjoint subsets means a state in one subset cannot be in another subset. So a state can only be in one subset. It cannot be shared by two subsets, right? So that all transitions are from one state to another state, from one group. It's not state, it's group. It's group. So for one group or one subset to another subset. So given a class of periodic states, we can further divide it in groups S1, S2, S3, so that all transitions, the arrows that we have, are from one state, one set of states to another state. They cannot be like this, or they cannot be like this, right? It's not allowed. All transitions have to be from one set to another set. There may be three sets. In this case, we have two sets. There may be as many sets as you can imagine. There can be any finite number of sets. In fact, if I mathematically, if I is a state that belongs to a subset K and Pij is greater than 0, this means there is a transition from state I to state J that is greater than 0. This means a transition line exists between states I and J. Then the state J is in Sk plus 1. I is in Sk. So J has to be in the next in the next group or in the next subset for k is 1 2 d minus 1. Suppose I is in state 1. If k is a 1, if I is in state 1, I is in state, I'm saying it wrong, it's not state, it's set. If I is in set 1, then j has to be in state, j has to be in set, j has to be in set s2. If I is in set 1 or group 1, j has to be in set or group 2. If I is in 2, j has to be in S3. If I is in S3, j has to be in S4. But what if I is in the last group or the last subset Sk? Then what's about j? If Bij is greater than 0, this means a line does exist between I and j. Then where should this j be? This is the question. Right, the answer is simple. Since these are periodic and all states like this, 1 to 2, 2 to 3, 3 to 4, 4, d minus 2 to d minus 1, d minus 1 to d, and all arrows from d, they go back to the first state. So the answer to this question is that if I is somewhere here, if I state is somewhere in this group, j would be in the first group. J would be in the first group because finally it has to complete the cycle. Right. So this is very important to understand this mathematical expression that is defined for periodicity, and periodicity is defined for a class of recurrent states. It's defined for a class of recurrent states. We have already told that. Right. Before we finish this, let's solve an example. Here is an example I have solved for you. In this example, let's bring this whole example in the view. Right, it is in our view. No, not now. Now, right, now it's completely in our view. We have these 6 states, and this 1 and 2 is a class of recurrent state. We call it recurrent class 1 because 1 and 2 are accessible from each other. Right, so this is recurrent class 1. 3 is a transient state. It's not recurrent because the arrow that is going to 4 from 3, there is no arrow coming from 4 to 3, so it's not recurrent. So it's not in order to complete this whole process, we need one more line that is from 3 to 2. That is from 3 to 2. Right, now this is complete. This is a set of recurrent class, and we call it, this is a class, this is recurrent class 1, which we have all the, oh no, it's still not correct. It should be like this arrow should be like this, right? And the direction of arrow isn't right now. Right now this is recurrent class 1, and this is of course a transient state. This is recurrent class 1, and this whole is another class of this whole is another recurrent class. We call it recurrent class 2. Right, for this recurrent class, this can be subdivided into 2 subsets, S1 and S2. Why? Because all the arrows that are emerging out of S1, they are going to S2, and all arrows that are emerging out from S2, they are going to S1 cloud. So these 2 clouds refer to 2 different subsets or 2 different groups, and this condition is fulfilled that If I is in one group j and Pij is greater than 0, then j has to be in the very next group. And if it is the last group, I is in the last group, j should be in the first group to complete the cycle. So here we have only two groups. So all arrows emerging out of the first group are landing in the second group, and all arrows from this second group, they are landing in the first group. So this is an example of periodicity that is found in this recurrent class 2. 4 and 5, they are packed in one subset, and 6 in subset 2. Right. So that's all for today's lecture. In the next lecture, we will continue studying Markov processes. Thank you.